Last time we stopped at the RL and source example, so we'll skim through that quickly and then we'll continue. So it's a full wave rectifier with an RL and a source. So we'll draw our full wave rectifier. My R, my L, and my DC source. And this is my AC source. And my output, the output is the voltage across the full RL and a source, right? My input voltage is like every time, it's a nice sine wave. The output voltage actually consider a case where we have a resistor and source alone. Okay, what would happen in that case? So what would the current look like? This is V input. This is my DC.
Zero until
Zero until it gets to the two sources are equal to each other, right? And then also when the AC source is less than the DC source, it's also zero, right? So I would have current here for the case of a resistor and source alone, right? And then the case of adding the inductor in there, I would start at the same place, right? But I would not rise as fast because the inductor does not allow the current to change as fast as a resistor does. So the raise of right is slower, and I'm always lagging, right? Inductors cause a lagging power factor, so the current will definitely fall beyond this point. Okay, it can fall here, or it can fall after that, right? If it tries to fall after that, this is a full wave rectifier. So with the resistor case alone, what was the output voltage with the resistor and source? What does the output voltage look like? The resistor and source. What does the output voltage look like?
What is the what?
It's the output voltage. Will it start at zero?
That starts when the current starts.
It starts at no. It's not. Does not start when the current starts. It starts at VDC, right? It starts at VDC because when there's no current flowing in this branch here, then the voltage between these two nodes, which is V output, is equal to VDC. So it starts at VDC, and then as soon as current starts to conduct, in the resistive case, resistor, so it will follow my input, right? Right, it will follow the input, and then here current became zero for the resistor source case, so it becomes like this. How about in the second half wave? This is a full wave rectifier, right? What's going to happen, okay, here until in a full wave rectifier without a DC source, I would have seen this output look like this, right? As soon as my power supply terminals are flipped, instead of diode 1 and 2 conducting, I have diode 3 and 4 conducting, right? So if 3 and 4 conduct, and I have only a resistor case, I get this dotted line, right? Resistor and a DC source case, what do I get?
You get the same thing.
This will continue here, right? Current is not flowing, so current is not flowing in 3 and 4. What is V output? Also equal to VDC, right? Current will not flow. As long as current is not flowing, output voltage equal to VDC. And then I get the same thing here, right? This is V output for R and the DC source. R and DC source, right? How about R? Any questions? Very fine. How about RL? RL and a DC source. where current actually stops here, right? What do we get? Initially, what do we get?
Same as DC.
Same as the previous case. There's no conduction before this point until the DC source is equal to the AC source. And then current starts conducting until this point here. So the input, so if current conducts, meaning diode 1 is on and diode 2 are on in the positive half cycle. So diode 1 will remain on, diode 2 will remain on for the duration of current conduction. So as long as diode 1 and 2 are on, then the output voltage is equal to the input voltage, right? So the output voltage will equal the input voltage all the way until here. And then current stops. If current stops flowing, then the output voltage is equal to VDC again, right? And we repeat the cycle. No? Ask. I mean, do you get the resistive case? Okay, so inductive case is exactly the same, except that we have to agree that there's current flowing in the circuit, right? If there's current flowing in the circuit, that means that the equivalent circuit that we have looks like this. And this is my V output that I'm looking for, and this is V input. So V input will equal V output, as long as there's current conduction.
So with different voltage, can we make it go beyond?
Of
zero?
course, beyond zero, this is a full bridge rectifier.
So
If you try to go beyond zero, diode 3 and 4 will conduct, like the previous case, and that's the other condition. So this is called the discontinuous current case, and then in the text they also show the continuous current case. So instead of the current stopping here, they show a case where the current starts rising and then never falls. Right? So this would be the continuous current case. In the continuous current case, what does the output voltage look like? So initially, it's the DC. Right? Obviously, anytime I don't have current, my output voltage is equal to the DC voltage. Right? And then, as long as I'm conducting in the positive half cycle, my output is equal to, this is my input. And my input rectified. Right? This will be my output equals my input because I have current flowing. Right? If I have current flowing, output equals input. This is a full wave rectifier. As soon as the voltage tries to flip, diodes 3 and 4 will start conducting. So 1 and 2 were conducting initially. Then 3 and 4 start conducting in the second half cycle because it's easier for the voltage to go to you flip the polarity. It's like flipping the polarity of the output voltage. If you flip the polarity of the output voltage, 4 finds it easy to conduct. 4 finds it easy to conduct, and 3 finds it easy to conduct. 4 finds it easy to conduct because this is the most positive voltage in the circuit. So 2 will block because you're putting a positive voltage here. 2 does not like to conduct. It's being opposed by a big positive voltage here. 4, this is a negative voltage, and this is a positive voltage. Right? So because I flipped the output polarity. So it will conduct. 4 will like to conduct. It's easier to conduct 4 than try to push 2 to continue to conduct. So 3 and 4 will automatically pick up as soon as you try to go to the negative. V output tries to go negatively. So we get something that looks like this. So on and so forth. Okay? Any questions on this? So here, the equation for current we've come up with before. We've seen this exponential rise and drop in current, and we know the point at which the DC voltage is equal to the AC voltage. That's the current inception point, and then that's the I of alpha equal to 0. right? That's I of alpha equal to 0. How do you find alpha? You equate VDC is equal to, so VDC as a value will be equal to V max, sine alpha for the sine wave. You solve for alpha. You have your inception point. So I of alpha equal to 0. And then, so in your equation for current, you have a forced response, and you have a natural response, exact same as the chapter 3 stuff, right? And then you will have a letter A, a variable A that is you find from initial conditions. And then if you want to find your average output voltage, you have to find your extinction point, current extinction point, which we call beta. How do you find beta? I of beta is equal to 0, and you find that from numerically because you don't have a closed form. Exactly like it's the same equation that we had in chapter 3. We just keep repeating it. Yes, ma'am. But one with a DC source, of course. We had one in chapter 3 with a DC source, one without a DC source. There are two equations. I mean, it's just one equation, but one of them you added the next version of it, you add a DC source. So there's just two versions of this equation. I mean, there's no other new equation that I can bring. These are the two equations that we have in the chapter. Yes? Okay. So this we have from before. So now if I have the equation for current and the output voltage in this case is something that we don't have a defined format for really. So if we want to come up with the average output voltage, we would have to integrate again Vmax, our original, Vmax sine omega t from alpha to beta, and we would know that from 0 to alpha it's equal to VDC, and from beta to pi it's equal to VDC. That's if you want to calculate your average output voltage. Yeah. How about in this case? So here we know the current equation, and the voltage equation is either DC or your input sine wave, right? DC or your input sine wave. So you can find its average value, RMS, whatever you want. How about here? Here the voltage equation is your sine wave. Forget about the transient initially, okay? We don't care about that. That's just one. After that, it's always like the full wave. So here your voltage is the full wave rectified waveform, but your current does not have a defined closed loop form. So what would we do here? Again, we start from the voltages Fourier series because it's a periodic waveform that is not sinusoidal, so we can find the Fourier series for the full wave rectified voltage waveform, and we divide that by the impedance of the circuit at every impedance to find the current at every harmonic. And then from there you can find THD, power, etc., etc. Right? I think we went through something like we talked about like something like this in the last class. So here its average value is equal to, of course, 2V maximum over pi will be the average value from the sine wave. If you go to your Fourier series, where's the Fourier series sheet? Fourier series of common waveforms. So this is here. This is a waveform, full wave rectified waveform. This is its Fourier series. Its average value is 2V max over pi. That's the DC value. And then first harmonic is minus 4V max over pi, cosine, blah, blah, blah. And then third, fifth, so on and so forth. Right? So, yes?
What decides if it is continuous or discontinuous line with
The value of RL and the DC source. So if you increase the DC source, increase the value of the DC source. What are you doing? You're moving this point to the left. Decrease the value of the DC source. You're moving this point to the right. Increase the value of inductance. You're moving this point to the right. Increase the value of the resistance and maintain the same value of inductance. Then you're moving the point to the left. Right? Because you're either changing the time constant, L over R. If you make the time constant larger, then you move to the right. You move this point to the right for a larger time constant. L over R larger, you move this point to the right. You move it to the right, at some point it becomes continuous. When this point gets to here, it becomes continuous. Yeah. So it depends on the time constant and the DC source. Good point, because there's a link that I have on the website here. It's called Interactive Power Electronics Simulation. It's instead of going and doing, you can go and do a simulation on PSIM or PSPICE or etc., etc. But this link here, it helps you understand some of these concepts without having to go and build a simulation. So they simulate it for you, They actually have their own free simulators called Gecko circuits, and you can download that and perform separate circuit simulation. But they also have the standard circuits simulated for you. So we're talking here about the full bridge, single phase diode bridge rectifier with a DC side inductance and DC side voltage. So here, if it comes up, here, it will come up. So here you can, they tell you here, they allow you to play with some of the parameters. So here they tell you, drag the vertical red time marker on the left-hand applet where the time behavior characteristic current and voltage of the circuit are shown. So this, if I drag it to the left and right, they will just, you know, so if current's not conducting, you know, the DC voltage is here, all the way up here, right? So before the AC and DC voltages become equal to each other, there is no current conduction. So I move the time marker, you know, right here is when we expect, you know, the DC voltage and the AC voltage, you know, are equal. So beyond that, right beyond that, the AC voltage is a little higher, so we expect the circuit to start conducting current. So this, the light blue waveform is what waveform? Waveform? And what's the dark blue waveform? The light blue is what? Yes, it's the load current. And the dark blue? Source current. Source current. Okay? And then the green is your input voltage, of course. And the gray is your input voltage rectified input voltage. So anyway, so you can move this along. So here, here diodes 1 and 2 are conducting. And then, you know, if you move this here, of course, current stops conducting, and then here, diodes 3 and 4 are conducting. If you bring down this point, you know, you're doing what? You're bringing down the DC voltage that's opposing current. This DC voltage is opposing current, right? So if you bring it down, you expect the current to increase, right? So you expect the current to increase. So as soon as the current reaches what? Reaches pi here. Right? As soon as the current reaches pi here, it becomes continuous. Right. So as soon as as soon as these 2 points, when these 2 points hit each other, they touch each other, then the current becomes continuous. Right. So at some point here, where right, it's hard to time it, but anyway, at some point these two, you know, this light blue waveform becomes greater than 0. That's where it becomes continuous, and the current becomes continuous at that point. I just had to decrease the value of the DC voltage source. Okay, and then of course, at some point, you know, you can look at what's happening to the input current waveform, the blue current waveform. Of course, the amount of harmonics in there has changed considerably. So I mean, play with this. It's nice. I mean, it's see here. There's no period where there's no current flowing in the circuit, right? So you move from diode 1 and 2 to diode 3 and 4, diode 1 and 2 to diode 3 and 4, all the time. So this is nice, and this is the case for the resistive loads. We won't go through that, but I mean, you can play with that as well. We will go through another one where output capacitor example, we'll do that. So any questions on this? Discontinuous mode? Good. These are just some simulations I did. And then now, for the output capacitor case, so similar to the half-wave rectifier, the objective here is to do what? We want to create DC with low ripple. How do you do that? You cannot merely do that with the circuits we've had before, because, you know, generally they have large ripple, huge ripple. From the minimum value of voltage to the maximum value of voltage is very large. So how do we deal with ripple reduction in rectifier circuits? We would typically put either a capacitive filter, or, as you will see later, we may add some inductance to it as well. and we discussed this for the half-wave rectifier, and the analysis is exactly the same. The only difference is we will find that the equation for the ripple voltage here includes a 2 in the denominator. So we need everything else is the same. You will find that if you go back to chapter 3, you will find that delta V is equal to V max over F RC. Here it's V max over 2 F times RC. So I need half the capacitance value to maintain the same ripple voltage that I had. Why is that? Because I've doubled the frequency. Remember we talked about the effect of frequency. So here in a full wave rectified waveform, I have doubled the frequency of the voltage that is being filtered by the capacitor. What voltage is being filtered by the capacitor? The full wave rectified waveform. Right? So the waveform here is without the capacitor. And then we've added the capacitor. What does the capacitor do? All the AC components for an ideal capacitor, all the AC for an ideal and infinite capacitance, all the AC components will go through the capacitance. What will be left to go through the resistor? The DC. Right? But this is not an infinite ideal capacitor. It's a finite value capacitance. So not all the AC components will go through it. Most of the AC components will go through the capacitor, and then some will pass through the resistor. Because some will pass through the resistor, we expect to see some ripple. We don't expect to see a pure DC on the output. Right? And the logic or the explanation we used last time we'll repeat this time. So there's a value of an angle theta here for the case where I don't have a resistive load, or for the case where the capacitor value is infinite. The capacitor was originally discharged, then it is charged through the supply until the peak value of the voltage, and then it remains at that peak value of the voltage. This is if the capacitance is infinite, right? Since the capacitance is not infinite, it's a finite value, and I also have a resistor here that will consume current. Then what will happen is there will be a point, at some angle theta after pi over 2 here, very small distance after pi over 2, there will be a point where the slope of this line, which is an exponential, this line is an exponential. Why is this line exponential? Because at some point, again, what I have here is a full wave rectified waveform. Right? This full wave rectified waveform, it reaches a peak value, then goes down. This capacitor is charged all the way until the peak value. Then, when this supply voltage tries to go down, it's trying to bring current out of the capacitor. Same logic we discussed last time. If it tries to bring current out of the capacitor, assume that this load does not exist for now. Then the current is going to try to go through these diodes, and the diodes will block, because all diodes here are pointing up. Current cannot go back. Right? So the diodes 1 and 2 will disconnect. So originally diodes 1 and 2 are connected, and they're charging this capacitor. Right? Then you bring the voltage down, it means you're discharging the capacitor. Discharging the capacitor means current has to come out. Current tries to come out, it blocks the diodes block it from coming out, and they disconnect. Right? That's if I don't have a resistive load. If I have a resistive load, and when does it do that? As soon as the voltage goes down below the maximum value. Right? So if I don't have a resistive load, as soon as the voltage goes down below the maximum value, finish. Capacitor voltage is higher than the source. So capacitor will try to discharge to the source, and the diodes disconnect. Now I add a resistor, so I'm consuming some current, right? So the diodes won't disconnect immediately, because the capacitor is going to be allowed to discharge now through the resistors, through the resistor that's connected there, right? So now the current coming out of the capacitor has a resistor to go to, so it will delay that disconnection for a little bit more, and that's where this angle theta comes into play, right? So that's where the angle theta comes into play, like we discussed before. So it's a little bit after pi over 2. Okay? What happens at that angle theta? Again, the slope of the input voltage and the slope of the capacitor voltage, they start deviating. So my equation for input voltage is Vmax sine theta. My equation for the capacitor voltage, again, this is an RC circuit. The current will have a form equal to will have a shape equal to AE to the minus T over tau. So A happens to be Vmax sine theta. That's A. E to the minus T over tau. There's a shift in axis. So I'm not starting at 0. There's a shift in axis of theta, right? So AE to the minus omega t minus theta over tau in this case. So this is AE to the minus T over tau. So at this point here, the slopes of these two curves will deviate. So like we did before, we differentiate the left-hand side, differentiate the right-hand side, and equate them to each other. And from there we found theta. I don't do that here. I don't think I show the differentiation here, do I? No, not here. No, this is not, no. I don't show the differentiation here. Okay. So here is these are the two voltages, the exponential and the input voltage. And then from the discussion that we had last time, we end up with an equation to calculate theta. So we calculated theta from the two slopes, right? From the two slopes, we calculated theta. And then we have to calculate what? What's the other angle we have to? I would like to be able to calculate the point at which this exponential intersects my input sine wave again. This point happens at pi plus alpha. Right, so remember last time I had two angles to calculate. So theta was easy, we did not have to use numerical methods. Right, we just differentiated both sides, both equations, equated them to each other at omega t equals theta. And we found theta. And it depends on the R and C values. And then we wanted to find, our objective is always to find what? What's the objective in this circuit? It is to find what? The ripple. My objective is to find delta V. So since my objective is to find delta V, fine, I know the peak value. That's no problem. I want to know the minimum value. How do I know the minimum value? For me to know the minimum value, I need an equation for this line. How did I find an equation for this line? I found an equation for this line by knowing, theta, the point where this line starts, and alpha, not a line, it's an exponential, where this exponential starts and where the exponential ends. Where does this exponential end? So this exponential ends at the point pi plus alpha. At the point pi plus alpha, the exponential equals my input sine wave. Right? So this exponential, Vmax sine theta e to the minus t over tau, is equal to my input sine wave. Right? But input sine wave where? At an angle of pi plus alpha, at an angle of pi plus alpha. At an angle of pi plus alpha of my input sine wave, with a negative sign, of course, because it's rectified, right? I have my exponential equal to it. And here I use the same t. Same t, it's pi plus alpha. Instead of my omega t here, I use pi plus alpha. And this is an equation that cannot be solved it has no closed loop form, so we have to use the calculator to find alpha. Right? Same exact logic that we followed last time. And then, in the case where you have sized your system properly, meaning you have not put a load here that will bring this theta all the way down to here, right? You can bring this theta down all the way down to here, and you will end up with output voltage waveform that looks like this. Oh, sorry. Right? In this case, you would have to find alpha from this equation, and then how would you find delta V? Delta V would be Vmax minus, exactly, minus Vmax sine pi plus alpha, because you would like to find the value of the sine wave at this point here. You have your sine wave, actually Vmax plus, right? Yeah, you can. Yeah, it doesn't matter. Pi plus alpha. No, because this Vmax pi plus alpha will give you this value. Same, right? If you get it pi plus 180, sine of something and sine of something 180 degrees later is no, it's there's a negative sign, right? So you will find Vmax sine pi plus alpha will be down here, right? So you have to be negative, so you put a negative sign, right? So this will be a negative number. Vmax sine pi plus alpha, it's something, alpha is an angle that is less than 180 degrees. So if you add sine 30 and then sine 30 plus 180, it's a negative number, right? So that's why you have to keep in minus sign here. Okay? But basically, you want to find the difference between these two. That's your objective. So to do that, I need alpha. And for me to find alpha, I need to find theta, because I need to find an equation for this exponential line. That's the logic, right? We had to find theta because we want to find the equation for the exponential line, which will at the end of the day give us alpha, which we need to calculate delta V. So this is one way to do the calculation of the ripple voltage if you have large ripple voltage. If you did not size your rectifier properly, right? In the homework, you saw something where they would tell you the circuit has a time constant equal to twice the fundamental period or something, right? Or it has a time constant, a low time constant, no?
There was one where you compare them.
Yeah, they will tell you, well, they give you 2 time constant for the circuit, right? Yeah, so it's similar to that. If your time constant is large enough, then it means that if your RC time constant is large enough, it means that you will discharge slowly, and hence you will not need to use the exact solution. There is an approximate solution that was derived in the textbook that you can use directly. But if you have a very small time constant, then you have to use the exact solution, which is this one. Right? So, and to do this, you have to calculate theta first and then alpha, and go through the full process. Right? So there are 2 ways to do it, like you saw in your last homework for chapter 3. The only difference here is, here we need a capacitor half the size. Why is it like that? Because we discussed the effective frequency on the capacitor size, I think last time or the time before, right? So here I've doubled the input frequency. Double the input frequency, then I need half the capacitance size to be able to do the same filtering. So any questions on this? Fine. Okay. Okay, now these are some special circuits called voltage doublers. So sometimes you would like, sometimes you have a voltage that, you have 120 volts at the input. Like if in the US system, you'd have a 120 volt input, and you have an appliance that is 240 volts, right? One way to play with that is put a transformer, right? Take your 120 volts, step it up with a transformer, and hook up your load. That's one way to do it. Another way to do it is that if you have a circuit that is able to double the voltage by itself easily, then that's a nice way to do it. But of course, this is producing DC; it's not producing AC. So it's something that it's a circuit that can be utilized inside your devices to be able to run. Sometimes some instruments would have a switch in the back and tell you, okay, switch it. This is 240 volt mode. This is 120 volt mode, right? At the end, a lot of the electronic devices inherently require DC. At the end, they all ask for DC because your microprocessors, your sensors, all of those require DC at the end, right? So, but your front end needs to be AC because we're hooking it up to the sockets in the outlet, right? So we're hooking up to here, these outlets. It's AC. At the end, I need DC. So sometimes there are nice ways to for example, create a twice the output voltage from a low input voltage. Is something you may like in a certain application. It depends on your application. So how does this circuit work? Again, it's a type of AC to DC converter. The rectifier still uses some diodes and capacitors. But how is it producing twice the output voltage? Any hints? Go ahead.
Two capacitors, both have charged to the end.
So this is my V input, okay? This is V input. So what's happening in the circuit? What's happening? Yes, Mariam, you were talking. Why are you
Oh,
quiet?
sorry, it's a full wave rectifier, but then, I mean, during each half cycle, one capacitor is charged, and then the next one is charged.
Okay, so during a positive half cycle, okay, so this is a positive voltage, negative, okay? So if this is the most positive voltage in my circuit, then this diode is seeing a positive voltage. How about this diode here? On this side, this diode is seeing a positive voltage here and a less positive voltage here, right? How about this diode? It's seeing a positive voltage on this side and a negative voltage, a less positive voltage here, right? So this diode is ready to conduct. This diode isn't ready to conduct, right? It does not have the voltage polarities across it to allow it to conduct, right? So if this top diode conducts, what is happening? Current will flow from the source through diode D1 and charge capacitor C1, right? Also, there's nothing that would prevent it from going through here, right? And then this capacitor is not charged to any value initially, it's discharged. So it's a capacitor with no voltage across it. So if I push, this is a capacitor. If I push current through it this way, and this is my polarity, then I'm charging it. If I push current through it that way, I'm discharging it. Right? That's exactly what I'm doing. So if current can flow through the capacitor this way, and then back to the supply. So in the first half, so I'm feeding the resistor in the output. I'm still feeding my load, right? The idea is I always have to feed my load. So here I'm charging capacitor C1 in the first half cycle. To what? I'm charging it to the same voltage as my input. Do we agree? I mean, I'm putting my input voltage across it. Right? I'm putting my input voltage across C1. Yes? And I can go through the same, it's like the capacitive output rectifier that we discussed before. I have it, but with a resistor in parallel. Consider there's no resistor in parallel. The capacitor C1 will be charged to the peak value. Right? If there is no resistor, at this point, capacitor voltage becomes higher than the input voltage and diode D1 stops conducting. Since I have a resistive load, then, and as soon as the voltage tries to go down, meaning I'm trying to discharge the capacitor, I have a resistor that this capacitor can also discharge through, so there will be a value theta a little bit behind pi over 2. Right? Same discussion. Right? But here we don't go, I mean, the book, in the textbook, we don't go through the analysis of this example. We just go through the waveform drawings. As an application of capacitive output rectifier, it's just an application. Right? So we've charged it to the peak value of the supply, and then assuming this resistive load is not, too small of a resistor to draw the current very quickly, then what's going to happen? What do we expect to see? Is this a half-wave rectifier or a full-wave rectifier? It's a half-wave rectifier. This is a half-wave rectifier that we've seen before, right? So the source, diode, and capacitor, right? I assume this is not there. Assume this branch is not there, and this is just a piece of wire. Then it's a half-wave rectifier. What happens in the half-wave rectifier? The half-wave rectifier, if I properly choose my capacitor to match my resistor value, I will discharge here, right? The capacitor voltage will go down, and then, in the next cycle, it will go back up again, right? Do you agree? Yes? No? Yes? Okay. So, and then the same thing with the other half-wave rectifier. But now I flip the polarity of the voltage. Right? If I flip the polarity of the voltage, then what is conducting? This is the most positive voltage in my circuit. This is the most negative voltage in my circuit, right? Then this is the most negative voltage in my circuit. Definitely this is more positive than it. This is the most negative potential. So this diode is able to conduct, and remember this capacitor was charged to a voltage. It was charged to a certain voltage. What is that voltage equal to? It was charged to my supply voltage. Right? It's charged to my supply voltage, and this capacitor is discharged initially. So this point and this point are zero. It's the same. There's zero voltage here across this capacitor, and now this capacitor C1 is charged to some voltage equal to close to my supply voltage. So what's going to happen to this diode? This is a negative voltage, and this is charged to my previous supply voltage in the positive half cycle, which was positive. So this diode will block. Right? So this diode blocks, and this diode now conducts. So current flows from my source here, here. What's happening to my capacitor current? Capacitor. Remember now, I am pushing current into the positive terminal. I'm charging the capacitor. Now in this half cycle, I'm charging the bottom capacitor. Charging it to what? To the same value as my supply voltage. So initially this capacitor was discharged, was all zero. This is VC2. Right? Initially it had a voltage of zero in the positive half cycle. And then in the negative half cycle, I started charging it. Right? I started charging it using my supply voltage. Until when? Until I reach the maximum value of my supply voltage again. And then, fine. It acts like a half-wave rectifier, so it will discharge through the resistive load after that. And then what is my output voltage? My output voltage is what I see from this terminal all the way to the top terminal. It's this voltage plus this voltage. These two capacitor voltages added together. Right? So initially what does the output voltage look like? So these two added together will look like this. Right? I charge to my input voltage, and then this is now almost equal to the input voltage. And now comes the second half cycle, and now the other capacitor starts charging. Right? And it stays up there. So one half cycle this will charge, other half cycle this will charge. Like this will charge, other half cycle this will charge. And then there is a slope to this that's going down. How fast it goes down depends on your selections of R and C. If you select it such that it goes down very quickly, you will never be able to build double the voltage. Yes, sir.
It goes down, but then it goes up once every cycle.
Yes, but if you bring it down all the way to, if you discharge this capacitor, VC1, if I bring this down all the way to here, then in the second half cycle, yes, this is charging, but then what is this plus this? This plus this is still equal to the input voltage by itself, not double. Yes?
I'm talking in the full bridge rectifier, the ripple happens twice every cycle. Here it happens once every cycle, right?
The ripple, I'm not sure, because I'm not sure what you're referring to, because
In the full bridge rectifier, the
Yeah.
ripple happens twice every cycle.
you mean the output voltage, this?
Yeah.
Yeah, here it's once.
Here
Here it's exactly like the half wave.
exactly.
So here you would size this capacitor based on the half wave rectifier equation. So it's V over delta V is equal to what? V max over FRC. Same as the half wave rectifier. Okay. So this is one example of a voltage doubler. Yes, ma'am.
Oh, sir, you said in the first half cycle, you said C2 was being discharged because it was flowing-
C2 was
because it was flowing-
originally it's not charged at all.
Okay.
Right? So if it's discharged, you will see that there's a little bit of a negative voltage across the C2, and This is a sort of a transient thing because it goes away right after that.
Okay.
Because after that, after this initial transient, there's no discharging of this. I mean, there's not much discharging of this anymore because this now is in the second half cycle, this built up a certain voltage, right? You now have a certain voltage value. When you discharge it, it will just go down here. It will go down after that. In the positive half cycle, it will go down, right? But initially it had a zero voltage.
Okay.
When this other capacitor was on, you were discharging this capacitor, this capacitor. So you would see that yes, this capacitor voltage was a little negative, and I have that in a slide actually. I have that in a slide. I just for me, since we don't care about transients too much, I didn't stress on it. But if we go back, if we go to the slides that I have, the simulation that I made, I show that somewhere here. Like D2 initially conducts, right, small negative until C2 starts charging. So D2 is here. D2 will initially conduct here. If this capacitor, once this capacitor is charged, can D2 conduct in the positive half cycle? The positive half cycle. In the positive half cycle, what's happening? This source is charging this capacitor, right? And then there is no voltage across this one, right? Actually, we put a negative voltage across this one, right? If I have a negative voltage across here, then this supply voltage is what? This is a positive voltage, right? I flip the polarity. If I flip the polarity of this capacitor voltage, then this diode will have a more positive voltage here than a negative voltage here at some point. But again, it's a transient condition. I mean, look at the simulation results. I mean, I'm not testing on transient condition. If you understand the explanation that I gave, positive half cycle, negative half cycle, that should be fine. But if you're interested, I added some simulation slides here that discuss the transient conditions. So go through them and then maybe do the simulations yourself, and then we can come discuss that. I mean, it's not part of the course. I'm just off topic here. Okay, so initially C2 is discharged, and it causes a bit of a dilemma. As soon as you charge C2 to a value, what happens? This diode will never be able to conduct because this is always positive with respect to this point. In the positive half cycle. And in the negative half cycle, it will conduct, of course. But in the positive half cycle, as soon as this capacitor is charged, that's it, you're done. It will be clear in this circuit, by the way. Let's look at this circuit. How does this circuit operate? It's very similar, but this problem that I was talking about will be clear here. Any takers? Yes, it's very similar. Come on. What's happening in the positive half cycle? So now I will have this switch. When the switch is open, well, how does the circuit behave? When the switch is open?
It's the same as the one above.
No. When the switch is open.
It's the double.
That's two capacitors in series and you have the capacitors.
But what is it like? What's the output voltage waveform?
Same as the full wave
Exactly. The output, it's a full wave rectifier. It's for the full bridge diode rectifier, right? The output is just this rectified waveform if the switch is open, right? Just because I put two capacitors in series, what is two capacitors in series? They have an equivalent capacitance and that's it. Resistors in series like capacitors in series. You just add the value. So if I needed certain capacitor value before, I live to get a certain ripple in the full wave rectifier here, I need half the capacitance, right? Capacitors in series are like resistors in series. No, capacitors in series are like resistors in series. Inductors in series like resistors in series. Sorry. Capacitors in series like resistors in parallel. So yes, you need double the capacitance in this case. Thank you. 214 is a very important course. I need to review it. Anyway, so this is my input voltage. And this is the output voltage when the switch is open, the full wave rectified waveform. How about when the switch is closed? When the switch is closed, here. Think positive half cycle, negative half cycle, same. In positive half cycle, right, this is the most positive potential, this is the most negative potential, right? And I think the simulations I was talking about was related to this diode D2 conducting, because now look at what's happening. This is current to flow through here, in the positive half cycle, go through and charge capacitor C1, also go through my load, right? And then back through, this is discharged, right? So current can come back through here, this way. It needs to go back through this terminal, right? Or it can go back through, it cannot go back through diode D4, because this is the most positive potential, so D4 is off for sure. But initially it can go through back through D2. It's an easier route if the capacitor is discharged, right? If the capacitor is discharged, capacitor is an impedance. Well, capacitor is an impedance, right? Transient, because I'm talking about transients, right? Capacitor in steady state is an open circuit, right? Or capacitor to DC is an open circuit. Here it's I don't have an AC high frequency current. I sort of have a low frequency current, so it will have a large impedance. This capacitor is a large impedance. So the capacitor will have to, the current will have to choose either to go through this large impedance or go through diode D2, right? So depending on the value of the capacitance and the value of the forward voltage of the diode, the current will go through this or that. That's only very in the initial transient, but in the second half cycle, so this is the positive half cycle. You agree? I charge C1. This is positive half cycle. I charge C1 using my power supply, correct? My source. And then what's happening? Capacitor C1 maintains the charge because it cannot discharge because these diodes will start blocking. And then it will discharge through the RC circuit. This output voltage waveform here will be like a full wave rectified waveform, not a half wave rectified waveform. But let's see. So now what's happening in the second half cycle? So, but we agree that at some point, fine, D1 will stop conducting, right? That's because the capacitor will have a certain voltage higher than the input supply voltage. The diode D1 will stop conducting. Everybody's fine with this? Same discussion like last time. Yes, sir.
You said, I'm not sure if you said that, do you mean a discharged capacitor has higher impedance than a charged capacitor?
No, it has nothing to do with charge or discharge. I mean, it's the fact that the capacitor is discharged in this case, right? So there's no voltage opposing the flow. So current has to split up between here and here, right? So current will see, okay, what opposes current? Impedance and voltage, right? The capacitor is discharged, so there's no voltage to oppose. There's just the impedance of the capacitor.
So it's a short circuit.
So there's no voltage, so current can flow here, right? But what do you mean it's a short circuit?
It has no voltage.
But XC is omega C. Initially, yes. Initially, capacitor current can flow through here. It will flow through both. Initially, it will flow through both. But again, at some point, how does it flow through both? It will divide up based on, the voltage, the reverse voltage that the diode is putting in place. And in the simulation, if you put that as 0, then what? If you use an ideal diode in the simulation, then all the current will flow through the diode, because this will have 0 reverse voltage, 0 forward voltage drop, meaning it's a voltage that opposes the current flow. And then this, as soon as current starts flowing through it, it will have an impedance. So current will choose which one is easier to flow. It will flow through the diode. So there will be initially some current flow through diode D2, only in transient, because what happens in the second half cycle? Second half cycle, what's happening? Second half cycle, let me erase this stuff. The switch is still closed. Switch is still closed. Second half cycle. This is the most positive voltage. Most positive voltage. Most negative voltage here. Right? So this diode will definitely not conduct. Right? And current will flow out of my supply and charge my capacitor and back through D4. D4? Yes. Okay? So we'll go back, charge this capacitor, go back through D4. So in the second half cycle I charged, so initially it's discharged, and then I charged this capacitor in the second half cycle. And then the full output voltage is the sum of the two as well, right? So then the full output voltage will look like, yes.
What about the C and the loop?
What do you mean? There is a voltage. So as soon as you start, okay, this is a resistive load, right? This capacitor has a voltage across it, even in the positive half cycle, right? And in the negative half cycle, it also has a voltage across. How about this? In the positive half cycle, it was 0, right? So current can still. So this is a voltage. What's the voltage across this? It's this voltage plus this voltage. So current will flow this way.
Right, so the blue current, there's also another loop around here.
There will be another loop around here, and it cannot go, and it will go discharge, I guess. Yeah, it can go discharge this capacitor as well, and that's what's happening here, right? So this we said the capacitor C1 is discharged. How does capacitor C1 discharge after the positive half cycle? Hmm? Through the resistor, it will discharge through the resistor, but it has to have a full circuit. So the resistor is seeing this voltage. This is a closed loop. This is a closed circuit for the resistor, right? So the current through the resistor will equal the voltage across the two capacitors divided by the value of the resistor. So his question is, what's happening to the current flow? The current flow, yes, in the positive half cycle, it's charging this capacitor. In the negative half cycle, fine, it's charging this capacitor, but it's also moving in the opposite direction of the current that was charging this capacitor. It's discharging this capacitor because it has to go through the load. Do we agree? I mean, it has to charge in one cycle, discharge in the other. Right? So it was this capacitor C1 was charging in the first half cycle. So in the second half cycle, what is it? I mean, current will have to be going in the opposite direction. Right? And it cannot go in the opposite direction back through the diodes, because these diodes are all pointing up. Right? So it's going to go in the opposite direction through the resistor. Yes?
This discharging does.
It's discharging the capacitor. Yeah, discharging. Yes, and it's here. We said that it's discharging the capacitor. Continues to discharge the capacitor. Until when? Until here. Right? Because it continues in the second half cycle. And the second half cycle is still discharging. Right? So, and here, because again, we remember this is acting like a half wave. This is not functioning at all. Did we even talk about D3? D2, we said initially there was some transient funky stuff that was happening with it, and then as soon as C2 is charged, as soon as I charge C2, D2 will never conduct. As soon as this is charged and this switch is closed, right? Then this is a positive voltage, this is a negative voltage. This will never conduct again. It only conducts in a transient. So simulated, it will never conduct. And how about this, the top one? In the positive half cycle, D1 is conducting. Right? How about the negative half cycle? D4 is conducting. D3 is not used at all. But this is exactly like, it functions exactly like this circuit here. But the only difference between this bottom circuit here and the top circuit is that this circuit can act as a full wave rectifier if we open the switch. It acts as a, this voltage doubler half wave when we close the switch. So it acts like the top one, exactly. Except that, there are some funky things that happen to D2, and I think that's what I was simulating. I was not simulating, if you go back here, yeah, I was simulating the full one, the full wave, the one with 4 switch, with the 4 diodes. And I was talking about the D2 initially conducting. And I zoomed in on diode D2 current. And then it becomes 0. Never conducts again diode D2. Okay? So any questions on those? Again, these are just applications of, yes, ma'am.
You said after they're charging, because of the polarity of C2, D2 won't conduct. But then once you have the negative polarity for the source at the anode for D2, with this,
Come again. So for this circuit,
yeah.
yeah.
So if the switch is closed,
Okay.
and then you said C2, you'll have positive and negative across the anode and the cathode for D2.
Switch is closed.
Yeah, and then C2 is charged.
And C2 is charged.
You said D2 won't conduct, but then won't the negative terminal of the source be more negative than the one at C2? There.
The negative terminal of the source be more negative than what? At C2?
Yeah.
But remember, this is a capacitor, okay? This, it will maintain its voltage. So it's like doing this. I've put now a supply here. I mean, it's like putting a DC, the battery. Like putting a DC source, VDC, and an AC source in series, right? And now you have your other circuit. Your other circuit is this diode D1, right? This is diode D1. You're talking about positive half cycle, right? Yeah. Yeah. Then I have diode D1, and then this will never conduct, right? Because I have a positive voltage here, and then it goes through capacitor C1 here and my load, right? This load, current, it's coming through from the source to charge my capacitor as well as going through the load. What's happening in the positive half cycle? In the positive half cycle, I'm charging C1, and I'm also doing what to C2? Did you remember, this is capacitor C2. I'm also discharging capacitor C2 because current is coming from my load, pushing current in the opposite direction of the charging for capacitor C2, right? So in the positive half cycle, I'm charging C1, discharging C2. In the negative half cycle, I'm charging C2 and discharging C1. As long as my time constants have been chosen properly, and I don't discharge any of them completely, then I can create this voltage doubling action. If I discharge one of them completely, if in the positive half cycle I charge C1, but I completely discharge C2, then I don't create the voltage doubling effect. Okay? Yes?
Over here, as opposed to the previous example, it has twice the number of ripples. Right?
It has twice the no, it's the same. I mean, same as the previous example. Actually, it's exactly the same.
One ripple per
Yeah. So here, let me. This is yeah. See, this is in one half cycle, and then this is the second half cycle, right? So in one half cycle, I charged 1, right, to the maximum. Then it discharges. It keeps discharging until when? Until the other one starts charging. In the second half cycle, and the circuit before was doing this. It was doing the same. In one half cycle, you were charging one and discharging the other. So here I'm charging this other capacitor in the second half cycle, and they add up to twice. And they both are discharging. Until when? Until a point here. I'm going to the positive half cycle again, right? But I've properly chosen my RC time constant so that, let's say, so this was my first capacitor being charged, right? It's going to discharge until when? Till here. It's a halfwave rectifier, right? In the positive half cycle, I'm charging one. Negative half cycle, I'm charging the other. So, and that's why here you will see this rising. There's a rise here again, because then you've you're starting to charge C1 again, the top one again in the positive half cycle. And here is when you see C2 being charged again. Here. Okay? And then correspondingly, anytime you're charging, what's going to happen to the current for C2 now? That C2 is being charged through diode what? D4? Yes, I don't remember which diode is this one. I'm trying to see what the blue current waveform is. The blue.
This is for diode 2, I think.
No, diode 2 is the red. It's this the capacitor 2 current. IC. This is This is IC2, capacitor 2 current. So capacitor 2 current. Anytime you are anytime you're charging it, we should see what this is happening. Right here, I started to charge capacitor 2. I started to charge capacitor 2 all the way until here. That's when this ends, right? Here I started charging capacitor 2 all the way until this point. Right? So this is capacitor current. It's positive when it's connected to the source. And then if you zoom in, this is actually negative. And it's discharging exponentially. And I think I have a plot of that. I don't. Capacitor current, I don't have a plot of the, I just have the initial section here. But in the, capacitor current initially is charging here. This is when you're connecting to this, when the diodes are connected. The diode is connected to the source. There is a positive current, and then the capacitor is discharging through the resistor. So this is the exponential, and it's negative. Here I'm exaggerating here. Exponential, and it's negative. It's discharging through the resistor, right? This is capacitor current. Okay, this is the bottom here is highly exaggerated. Okay, so now this is the voltage doubler stuff. Okay, this circuit here goes back to here. What's happening? We said that this is capacitor current. Capacitor current is equal to what? IC is equal to C dVc by dt, right? As soon as I start, remember the capacitors were discharging, and then they start charging at some point, depending on the value of the ripple that I've designed for. Here, the capacitor, the slope of the voltage was negative. Here, the slope of the voltage was, there's a significant change in slope of the voltage, and that's why we said we saw these spikes in current, right? So at this significant change in slope, I see a large value of capacitor current, right? And that explains the spikes that we had in capacitor current. The spikes in capacitor current are going to go through where? This capacitor current is coming through the diode to charge the capacitor, right? Or through this other diode to charge this capacitor, right? Which means that if the capacitor current has these large spikes, then the source current has these large spikes, then these diode currents have these large spikes, right? Which is a problem. You don't want to buy a device with a high peak current, or you don't want to have installed cabling and circuit breakers with high peak currents, and when you really don't need that, right? If you're delivering a certain amount of average power, that average power would actually depend on the area under the curve of the current curve, because it depends on the RMS value, right? So one way to deal with that is to put an inductor. Instead of putting a capacitor by itself, you create a LC filter, you put an inductive filter. What does this do? If you add an inductor and not just a capacitor, what happens is that these current spikes that we were seeing on the capacitor current are now filtered. So before we were seeing something that looked like this. or sorry, I should have done this, right? Because they start at the same point. Capacitors will start charging at the same point. But now I don't see, if I put this inductor here, the inductors don't allow very large variation in current. The time rate of current change has to be reduced if I put an inductor. So I end up with the current waveforms looking like this. This will deliver similar area under the curve. So similar power will be delivered to the load, but with a much lower peak value of current. So it's better for you because you buy lower switch rating for equipment rating. Yeah. So you typically buy devices, circuit breakers, cables, etc., based on average current rating as well as peak. You have to consider both, right? So here you'll be able to buy cheaper equipment, basically. So this is something we typically utilize. We typically utilize an LC filter, not just a pure C filter, unless you're talking about very low power. So typically we'd use an LC filter. So, and then I did some simulations. So this is, I just want, this is what they've discussed in the chapter, and the reasoning is what I discussed about, lowering the current rating of the devices, etc., etc. And here I just, wanted to simulate it to show you the more detailed simulation. So I did this simulation with PSIM, and of course this is the inductor current, and of course what happens, this inductor current is going to go through the capacitor. So I just drew inductor current and capacitor current just to show that this inductor current is going directly to the capacitor, right? And it makes, here, this inductor current, most of it is going to the capacitor. Some of the inductor current is going to the load, but most of it is going through the capacitor, and that's what we see here. This inductor current is going through the capacitor, most of it, but it's shifted a little bit. So you find that this peak is different than this peak in the negative. It has to be shifted because the capacitor is also feeding the resistor. So the average value of the resistor current and the capacitor current is equal to the average value of inductor current, right? The inductor is feeding both the resistor and the capacitor. So the average value of the inductor current is equal to the average value of the resistor and capacitor currents together, right? So again, these are waveforms. Draw the waveforms, simulate the waveforms. You have to make sure you understand the waveforms. You will be asked to draw waveforms in the exam and quizzes. So more simulations here. Not very important simulations. And then I think, so next time we'll start with the controlled full wave rectifiers, and we'll do 3-phase after that. So stop here.